Hello, this is my third lecture of so many lectures on the acid-base unit. Yeah, I don't know how many they're going to be. You just have to suffer through all of them. And this one is on the second page of the notes here, which is pretty much all problems because this is the unit of mathematical sufferings. So here we go. Let's get started on doing some of these, and let's see how long we last. How long are we going to last? There's no way to tell. All right, so pH problems are something that you sort of run into all the time, and they're very standard, and you just sort of got to know how to do them real fast. So we're going to do some of them. And so for these four, I have asked you to calculate everything given one piece of the puzzle, and this is the kind of square deal where you can go from pH to POH to OH minus concentration to H plus concentration and go walk around the square and neener. So given one thing, get the other three. So let's go to my black screen. All right, if you have got hydroxide concentration equal to 1e to the negative 5 molar, you need to remember your little square. Let's remember our square, we're going to need it. You've got pH and POH. And to move between these two, you have to remember the fact that when you add them together, it equals 14. Okay? And you've also got your pH and your H plus concentration, and you need to remember that to move between those two, to go from H plus to pH, that's negative log of H plus gets you pH, and to get from pH back to H plus concentration, that's 10 to the negative power, whatever the thing is. We'll do it, don't worry. And the same deal with the POH and the OH minus concentration, the hydroxide concentration. Between these two, to move between them, you go up to POH is negative log of the OH, and this is 10 to the negative POH. Will give you your OH minus concentration. So let's actually stick in here pH. And then between these two, if you want to walk between your hydrogen ion concentration, which is, remember, the same as your hydronium ion concentration, is the same deal. This is just after it has attached itself to a little water for fun. And your hydroxide ion concentration, to get between those two, you have to remember that when you multiply them, they equal 1e to the negative 14, which is pretty similar to this because this is just the logged version. And so the logged version is telling you the exponent, and the unlogged version is you've got to do it in exponents. Okay, so if you have this for your OH minus concentration, what's your POH?
Your POH is 5.
It's 5. And what that's asking is negative log of OH minus concentration, so negative log of this thing. And a negative log of 0.0001 is basically saying, well, how many decimal places are we off? And the answer is 5. So that's POH. So the POH is 5 in this case. You can't do it if it's something besides 1.0 in your head. You can figure out between which two numbers it's going to be. So if it was 2e to the negative 5, you know that it would be between 4 and 6. But you wouldn't really be sure where it would land exactly. You'd have to think about it pretty carefully. But the ones with ones you can do in your head easily. So your POH is 5. So what's your pH?
Is
9. How'd you do that? Well, they add to 14, according to this doohickey here. And in order to get to your H plus concentration, you can either get there using your pH or your OH minus. What do you want to do? What is your H plus concentration?
It is 1e to the negative 9.
It is 1e to the negative 9. That is correct, because the pH equals 9. What that's telling you is, hey, what's this exponent after the negative thing in the H plus concentration? It's a 9. Okay, so they're all those three. Same deal with these guys. Oh, by the way, is this acidic or basic?
This is basic.
That is basic. The pH is above 7. Bing. And also, there's more the hydroxide than there is hydrogen ions. So in B, we've got 1e negative 7 molar hydroxide. So what's your POH?
7.
7. What's your pH?
7.
7. And what's your H plus concentration?
1e to the negative 7.
Oh, yeah, no, that's right. 1e to the negative 7. I got you. I almost got you. You're like, wait, no, did I do it wrong? No, you did it right. Good job. Good job, assistant.
I can
Phew.
add.
Yeah, well, I can't. Okay, so what's fancy about this situation here?
It's equal.
It's equal. The concentration of hydroxide is equal to the concentration of hydrogen ions, which means that this is a situation in which it is
In equilibrium. Neutral.
Neutral. You guessed correctly. It's neutral.
Neutral.
Yeah. All right, this one, 10 molar hydrogen ions. That's pretty big, right?
Yeah.
Yep. So that's going to be, I like this one.
What question are you asking?
Oh, yeah, hey, what's the pH?
There we go. So that's going to be -2.
Well, how are we going to do it if we stick it in our calculator? We should be able to do it in our heads, but maybe it's making us explode.
Yes.
Yeah?
Yeah, it's making me explode.
Okay, what do we put in the calculator then?
Negative log of 10.
Negative log of 10 is?
Negative 1.
Negative 1.
So you're moving the decimal place 1.
Because if you, this isn't in exponential form, and so it's sort of hard to figure out what the exponent is, right?
Right.
So this in exponential form is 1e, is 1 times 10 to the first power,
Okay.
which is 1e1.
Okay.
The negative log of that
Is -1.
is -1.
There
So
you go.
our pH is -1, but that's extraordinarily low. Well, yeah, you're dealing with 10 molar acid. All right, so what is our POH?
Don't drink it. It's going to be 15.
It's 15. And what is our hydroxide ion concentration?
1e to the negative 15.
That is correct. And is that big or small?
It's really small.
Yeah, it's very small. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Bing. It's very small. Uh-oh. Do we have a squeaky baby? I am hearing some squeaks. We will have to return to this at a later time. Okay, we fixed the baby.
Wah.
Here we go. Blood. So we have blood, and the pH of blood is 7.41. Apparently, is that so?
It is so, actually.
That's good.
When it's normal.
When it's normal, unlike you.
I'm a vampire.
Do they have normal blood?
I don't know. I'm a human doctor.
All right. So pH 7.41. Do both ions. So what we can do here is take this pH and unlog it to get to the H plus concentration by doing something like this. 10 to the negative 7.41. And what that equals is it tells us the H plus concentration is 3.9 E to the negative 8 molar is your H plus concentration. And from here you can get from H plus to OH minus by doing 1E negative 14 divided by that guy. That's your OH minus, which is 2.6 E negative 7, and that's your hydroxide ion concentration. And your POH, you can either do it from here or from here, and that's 14 minus, so that gives you 6.59. Bam. And that's this first box. In your second box, you've got these three problems. 0.1 molar nitric acid, and it asks you to calculate the pH. What you got to recognize is that nitric acid is one of our 8 strong acids, and so when it tells you that the strong acid, nitric acid, is 0.1 molar, the H plus concentration is 0.1 molar, so that's negative log of 0.1, which is 1E negative 1, so that's a pH of
-1.
Nope.
1.
1. Yeah, this negative takes off that negative. Yeah, so the pH is 1. Here we have 1e negative 10 molar hydrochloric acid. You recognize this is another one of the strong acids, so this is the concentration of hydrogen ions because all of it has dissociated, and so that's negative log of this, and so the pH is 10. So what that's showing is that this is basic because the hydrogen ion concentration is less than 1e negative 7. And here we've got some sodium hydroxide at 0.2 molar, and that's going to be a little bit more than 0.1 molar sodium hydroxide. And so what we could do is we could kind of mentally, if this was a multiple choice question, we could go, well, 0.1 molar sodium hydroxide is a POH of 1, so a pH of 13. So it's somewhere close to this, but because it's a logarithmic scale and it's 10 times every time you jump up, it's hard to tell what 2 times is. So it's pH 13. It's a bit more basic than that. So it's 13 point something. So that would get you enough in a multiple choice question. But this is a strong base because it contains OH instead of having an amine something or other. Because it contains OH, all of it is dissociated just like the strong acids. And so you can do the negative log of 0.2 to get your OH minus concentration. And that gets you, to get your, to get you your POH.
There we go.
Yeah, you were like, what is she doing? Yeah, she's crazy. And that gets you a pH, a POH of 0.698, which leaves you with a pH of 14 minus that, which is 13.3. Okay, so that's the kind of thing that you are maybe going to have to do just off the top of your head in a multiple choice question, that kind of thing. Figure out what's the pH of this, what's the pH of this, what's the pH of this. It's a lot harder to do with weak acids because you have to run through all of the equilibrium hoo-ha. So you're typically going to see that question with strong stuff, not weak, as a multiple choice question. All right, weak acid problems. You've got to consider your Ka.
Here we go.
So this is the first example of kind of the big kind of type of problem that you're going to have to know how to do. So last time, the last lecture, we did a big, long, strong titration problem, and this is to introduce how to do a big, long equilibrium problem, which is going to involve a weak something or other. Okay. We need to calculate the pH of this solution, which is 0.3 molar hydrocyanic acid. And if this were a strong acid, you could just say, oh, well, the H plus concentration is 0.3 molar. It's not, because a weak acid does not dissociate 100%. It actually only dissociates a very small percentage. So you don't have a pH as strong as acidic as you would if all of the H pluses were loose from this. Most of them are still attached. So what you've got to figure out is, well, how many of them are attached and how many of them are loose, and that's what you use this for in your ice chart. So to begin with, one thing to consider is that when you're dealing with a weak acid in water, you need to consider this. You're dealing with this equilibrium, and you're simultaneously dealing with water's equilibrium. And sometimes when your weak acid disappears, suddenly your pH is being driven by the water's equilibrium again. So you need to kind of write down you need to figure out which equilibrium system is actually relevant. And the one that's important is the one with the largest Ka, the largest K. So this one is 6.2 e to the negative 10, and this one is 1 e to the negative 14. You can see that this one is 4 decimals less important than this one. So that's kind of 10,000 times less relevant. So we need to account for it. No, you don't.
Yeah,
So there's a significant enough difference that this one is the dominant equilibrium. This one would show up and be relevant if, for example, all of this stuff disappeared. All right, so we got to write an ice chart for our dominant equilibrium, which we should remember from our equilibrium lectures.
Don't forget you want space for the next problem. Is all I'm saying.
Yes, well,
I'm the assistant.
why don't you plan everything perfectly?
Okay.
Okay, I'll do it. I'm great. Okay, so what we got is 0.3 molar hydrocyanic acid. And when you start off before everything goes to equilibrium, you don't have any of those. You're going to lose a little bit of this. You're going to gain a little bit of this. And this structure shows up a lot, where these are both X, and they start at 0. So you end up with a x squared over 0.3 minus x, point something minus x would be typical, equals your Ka, which is 6.2 e to the negative 10. And then you solve for x. And what's nice is your Kas are all small. And so we learned back in the equilibrium unit that typically you can ditch this type of x if this number is smaller than about e to the negative 5. And they usually are. And even there have been a couple examples where it's like e to the negative 4, and I've kind of wondered, oh, can I get away with this? And I'll try it and find out, yes, it is. In fact, it's 4.5%, so that's less than 5%. So you still have to check your assumption. So we can assume that that x is irrelevant, so then that's 6.2 e to the negative 10 times 0.3 equals x squared, and you square root both sides. And so you end up with, if you do all your algebra, your x ends up being equal to 1.36 e to the negative 5th. Check your assumption. You've got to check your assumption. So is x in fact less than 5%? So that's going to be 1.36 e to the negative 5 over the thing you subtracted it from, 0.3 times 100. And it gives you 0.004%. So there's my assumption checking, and I win. So that means I don't have to go back and redo all my algebra the long way. Hooray! So that's x, and x, if you look, is the H plus concentration.
Hooray!
And that's how these typically work, is you solve for x and bam, that's your H plus concentration. And so if the question, which is typically asking what is the pH, you go, okay, well there's x negative log of that guy. And what that gives us is a pH of 6.59. And what you can see is that when we were dealing with our strong acids, we were dealing with pH answers that were like -1, 2, 1. And when you're dealing with weak acids, you're dealing with pHs like 4 and 6.5. They're weaker. They don't have as much effect on the pH, driving it to be so acidic. So there's your first example of doing these. We're going to do like a bajillion of them. Yay, I love that number. Okay, good. And then one thing to know is that when you're dealing with a weak acid, the amount that it dissociates in the water is actually related to how concentrated it is. If it's a low concentration, if you've got like a 0.1 molar solution, more of that acid dissociates percentage-wise than if it is concentrated. If you have a 10 molar solution of acetic acid, this is our example here, more of it dissociates when you have a low concentrated solution. When you have a high concentrated solution, you have so many H pluses that it drives the equilibrium to the left, according to Le Chatelier's principle. So here's acetic acid, and I'll show you what that looks like. Here's acetate, which, by the way, is maybe the most common organic acid instance that you're going to run across. So you probably should just go ahead and memorize that it's 232, because otherwise you have to check up and down all the time. It drives me insane. So when you have a dilute solution, you don't have that much of this in the concentration. But when you have a concentrated solution, you've got more H pluses. And when you've got more H pluses, that drives it left. And so you end up with less dissociation when there is a higher concentration. And here we're going to actually calculate how much is dissociated. For example, 1 molar acetic acid is only 0.42% dissociated, which is remarkably small because 1 molar hydrochloric acid is 100% dissociated. This is little. And when you've got 0.1 molar acetic acid here, is that going to be more or less dissociated? Less. Less? No.
More dissociated.
Yeah, you got it right the second time.
The second time.
Yeah. So let's go over this again because apparently it's confusing. When you're more concentrated, there's enough H's that it drives you left.
Right. So if you're less
when you're less concentrated, then you drive it to the right. So you're more dissociated in this case. Okay. So we'll see how much more dissociated we end up with. Maybe it's like way dissociated. I don't know. We'll see. Anyway, so here's my ice chart. Ding, 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 ding. And what do we have? 0.1. So that's 0.1. You don't have any of this. You don't have any of this. Minus x plus x plus x. 0.1 minus x, x, and x squared over 0.1 minus x equals, what is it? 1.8 e negative 5. And actually, acetic acid is so common that you end up memorizing its Ka. I'm like, oh yeah, that one. You can discard your x. You have to go back and check for it later. Is x less than 5%? We'll find out. That times 0.1 is 1.8 e negative 6, by the way. And then you square root it. So 1.8 e negative 6 equals x squared, because this is 1 decimal off. And so that's 1 decimal off as well. So square root, and your x ends up being 0.00134, which we stick in our checking doohickey, and we find out that x was only 1.34%, so we're good. Check. And so x is 0.00134. That is our H plus concentration. Now that we know our H plus concentration, we can calculate the pH, but that's not what we're asking, is it? No, it is not. We want to know the percent dissociation. So that's part over whole. So the part that is dissociated is 0.00134. The whole is 0.1, and this is a percent, so times 100. And so what's actually funny is that your calculation for percent dissociation is exactly the same as your x is less than 5%. And that happens all the time.
That's ironic.
Like every percent dissociation problem, you go back and check your x equals less than 5%, the answer is the same as what is the percent dissociation. It's something I've noticed. It's sort of funny. Anyway, so it's 1.34% dissociated. Is that what we expected?
Yes.
Yes, it is slightly more dissociated when it is less concentrated. So in your notes, this little blank here that you've got, dilution causes more dissociation. Okay? Okay. All right. Now, I know what you're excited about. You're excited about this problem here on the back, which has parts A, B, C, D, E, and F. You're excited about that part?
Not fair.
You love it. You love it.
I love F's.
You love F's. Well, all right. Consider the titration of 100 milliliters of 0.2 molar acetic acid. This is a lot like the titration problem that we did in the previous lecture, but that was all stoichiometry. This is stoichiometry and equilibrium.
It's going to take a while.
Yeah, it's going to take, well, we were 24 minutes into the lecture. Let's see how long it takes to do this problem.
It's going to be great.
I know, you're going to love it,
It's
children.
kind of cool.
Consider the titration of 100 milliliters of 0.2 molar acetic acid, there's your Ka, by 0.1 molar potassium hydroxide. There's your strong base that you're titrating with. You wouldn't titrate a weak with a weak. That would just be sort of pointless. Calculate the pH of the resulting solution after the following volumes of potassium hydroxide have been added. 0, so before you start, 50, 100, 150, 200, and 250. And again, we're going to run across the equivalence point, and we're going to run across after that when the strong base is driving the pH kind of. So we're going to, these are all different little situations here. So at 0, A, all you've got is a weak acid. This is just like that problem we did on the front. So let's do it. HC2H3O2. Look, I got it memorized. H plus and C2H3O2. Now what do we got? 100 milliliters of 0.2 molar. So the thing, remember, the thing here to remember, what goes in your ice charts is molarities. Molarities. Not moles.
Moles.
So the 0.2 molar acetic acid, so that's 0.2, that's nothing and nothing, minus x plus x plus x, 0.2 minus x, 1.8 e negative 5 equals x squared over 0.2 minus x. Kill the x. X is less than 5%. We'll come back to you. 1.8 e negative 5 times 0.2 square rooted. And we find that x ends up equaling 0.00190, and we take the negative log of this because that is our H plus concentration. And weird looking brackets, don't you think? And we find that our pH is 2.722. And you have to remember sig figs. pH decimals are concentration sig figs. My concentration is 0.200, that is 3 concentration sig figs. That means I want 3 decimal places in my pH. So pH, that was part A. Part B.
Do you do your 5%?
Oh no, I didn't do my 5%. I'm so bad. Thank you, assistant. 0.2, 0.00190 times 100, and that gives me, I didn't even do it on my paper. I'm so bad. Bad. I lose 1 point on my test, by the way.
Oh.
But I don't want to check my assumptions. You must always check your assumptions. Alright, that's 0.95%. But you didn't do it. Yeah, well, I'm in trouble. So, that's good. Bam. Alright, B, 50 mils. Alright, 50 mils. What we're doing is we are dropping base into acid. They're going to neutralize. There's going to be a reaction, and then there will be equilibrium. First, you have to do the math for the reaction. That's going to be the acetic acid and the potassium hydroxide, and that gives you water and salt. And the salt in this case is potassium acetate. And this is not an equilibrium chart. This is a stoichiometry before and after chart. The things that go in a stoichiometry chart are moles.
My brain's hurting.
I know, poor brain. And we're only on the beginning of B. All right, so what we have is we need to know how many moles goes here and how many moles goes here. So that's going to be 100 milliliters of acetic acid solution. I'm going to just write it that way. And this is our solution equality. And there's 1,000 milliliters of acetic acid solution. And the acetic acid solution has a concentration of 0.2 moles per liter. Acetic acid. So that's going to be 100 divided by 1,000 times 0.2. That's 0.02 moles of acetic acid. So that's 0.02 moles. The KOH you do similarly, which is 50 mils of KOH solution. And that's 0.1 moles of KOH present in every 1,000 milliliters of KOH solution. And so that's 0.005 moles. Okay, none of this and 0 of this. That's before the reaction. After the reaction, all of this is gone, right?
Right.
And 0.005 of this is gone, so that's going to leave us with 0.015 moles. And we don't care about water, and we have gained 0.005 moles of this. Now, this number is relevant and this number is relevant, because now that we have this acid and its conjugate base in solution, we need to figure out where it is going to lie in its equilibrium after this has happened. So we are going to fill in an ice chart now for acetic acid. So that's acetic acid. I know this is mind-blowing, isn't it? H plus and acetate. And initially what we have is, and remember in your ice chart you have to put molarities. We have 0.015 moles and how many liters? Well, we had 100 mils and we dripped in 50 mils. So we have 150 mils, so that's 0.15 liters. Okay?
Okay.
We don't have any of this at the beginning, but we do have some of this. We have 0.005 moles also in 0.15 liters. Okay? How does that make you feel? Terrible. And this ends up losing some x, this is gaining some x, and this is gaining some x. When you divide this out, 0.015 divided by 0.15, that's 0.1 minus x, and this is x, and 5 out of 15 is a third, so this is ends up being 0.0333, etc., plus x. So what you have is, again, this is acetic acid, so it's 1.8 e to the negative 5 equals x, and this is the case in which it's not x squared.
Right.
You're running across x squared a lot, but not here.
Right.
X 0.033 plus x, well, several threes, and 0.1 minus x. We get to drop some x's, which is nice. And we need to check to make sure that x is less than 5% when we finish. And 5% of the small one, by the way, so 0.0333 times 100. We'll go back and look at that guy in a bit. And so that is 1.8 e negative 5 equals x times 0.03 over 0.1. And you end up solving for this. That it's you multiply by this, you divide by this, and you get x equals, what is it? 5.40 e to the negative 5th, and x is still, luckily, our H plus concentration.
Right.
And so we can take the negative log of 5.4 e to the negative 5th, and that gives us a pH equal to 4.268. Again, 3 sig figs, 3 decimal places in your pH. That was B.
Check.
Oh, check. Check, 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 check. I'm in 4 e negative 5, and that gives us 0.16%. So
We're still okay.
we're still okay. Check. Okay, that was B. Here's, oh, we ran out of space. Where's C? C can be up here. C. How much do you add for C? 100 milliliters. So this is 100 milliliters of 0.1 molar KOH added.
There's going to be a trick, isn't there?
Is there a trick? This one is actually straightforward, I think.
No.
No, this one's got a trick. This one's...
See, I knew it.
Yeah, I know, right? Okay. This is do the stoichiometry first and then the equilibrium. Again, just like we did with B. So, just like we did with B. HC2H3O2 plus KOH yields water and salt. Before and after. And that's going to be, and I'm going to start skipping the steps required to show you how to fill this in, because you know that now. In your B4A4 chart, you need to show the moles, and that's doing that little stoichiometry problem, the milliliters of solution times the solution equality, because seriously, this is going to take forever if I start showing you every single step for all of these pieces. So this is 0.02 moles. It's going to be 0.02 moles every time, because they're saying, you know, after 100, what if you did 150? What if you did... So anyway, and this one is 0.01 moles. When you've got 100 milliliters of 0.1 molar, it's 0.01 moles. This gets used up. That's 0. This gets half used up, which that should make your brain have alarm bells. And you've got half of this. So you've got 0.01 moles of acetic acid and 0.01 moles of acetate, which in your ice chart, which you do, and you use these numbers to fill it in a second. Here's your equilibrium of acetic acid, which is what happens after the neutralization by the base. You've got 0.01 moles divided by the number of liters that you have now, which is 0.2 liters. This is 0. This is 0.01 moles divided by 0.2 liters minus x plus x plus x. And this ends up being 0.05, by the way, 1 over 2, right? 0.05 minus x. This is x. This is 0.05 plus x. And the math ends up being really pretty. 1.8 e negative 5 equals x times 0.05 plus x divided by 0.05 minus x, which you cancel your x's, and well, heck, you can cancel, look at that, 0.05 over 0.05. When you have the same amount of acetic acid as you have acetate, what you have reached is your half equilibrium point. We talked about our half equilibrium point. There's a special little calculation that you can run at the half equilibrium point, which is x is equal to the Ka, which means that your pH, which is the negative log of H, is equal to your pKa. So when you get to this spot, if you remember, you don't have to do this. You go, oh, they're equal. That's my half equivalence point. My pH is my pKa. I can just take the negative log of my Ka, and that will be my pH, and in this case, it is 4.745. Oh, also, probably my head is in the way right now. There we go. They complain about that. My pH is equal to my pKa. The negative log of my Ka is 4.745. That's the pH. Bam. So when you're at your half equivalence point, that is important. Now,
do you have to check for your 5% rule?
Yeah, I do. Yeah, you're so right. Where did it go? Up. Yeah, 5% rule. So that's going to be 1.8 e negative 5 over 0.05 times 100, and that gives me what percent? 0.036%. We're good. All right.
Now, would you have to check that if you knew that was your half equivalence point when you're looking for your pH?
It depends on your Ka.
Okay.
And it depends on how big this number is.
So check it.
Yeah, you got to check it.
Dang it.
I know, right?
I tried, guys.
All right.
I did.
Here's the good news. D is exactly the same structure as B. So you have all the skills to do D. Do D yourself. But I don't want to do D myself. Well, if you get it right, you'll get this for the pH. Take that. All right, E. E is slightly different. Are you excited? Yes, we love it when things are different. All right, E is 200 milliliters of KOH, which is 0.1 molar. So you do the stoichiometry, which is, where are we? E, the acetic acid and the potassium hydroxide, and you get some water and some salt. It's potassium acetate. This is before and after. And here's your acetic acid, which is still 0.02 moles, and your potassium hydroxide, which in this case is 0.02 moles. Do you see what this is? Do you see what is this? Do you know what this is yet, assistant?
This is going to be when we neutralize everything out.
When we neutralize everything out, it's called something in a titration.
The equivalence point.
This is the equivalence point. Isn't that nice? Here's the equivalence point. This gets used up. This gets used up. There, we don't care about water. We've got 0.02 moles of this.
I like zeros.
Now, at the equivalence point, things get sort of interesting, because if you're not paying attention, you're going to go and do this ice chart. and you're going to have acetic acid and
Except
acetate, except there's nothing
there's
here.
zeros, which isn't
So the
gonna
question
work.
of how much acetic acid dissociates is a sad question because there isn't any. So you actually have to change it to where you're doing the equilibrium from the perspective of its conjugate base.
Oh.
Okay? So that one goes like this. So at the equivalence points, you have to switch your equilibrium to the conjugate base. Well, what does the conjugate base do? We have to think back to our definition of Bronsted-Lowry bases. What do Bronsted-Lowry bases do?
Bronsted-Lowry bases donate an OH or
No, those are Arrhenius bases.
sucks up an H.
They suck up an H. Where's he going to get an H from?
Water.
Water. This guy is strong enough of a base to steal H pluses from water. They attack water. Weak bases attack water. Isn't that nice? So here he
That's
goes,
very nice.
attacking water. And so then we're going to make acetic acid once he has attacked the water. And some hydroxide. Look! This is a weak base because its action of attacking water increases the amount of hydroxide.
Uh-huh.
I know, right? So here's our equilibrium. Boom, 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 boom. 0.02 moles, so that's 0.02 over, how many milliliters are we at now? 200 plus 100, so that's 300. So 0.3, we don't care about water. And acetic acid, we don't have any. And a hydroxide, we don't have any. And we're going to lose some and gain some and gain some. And so that's, what are we in E? So this is 2/3, so that's 0.0667 minus X. This is X and this is X. Now, so you set up your equilibrium expression. You've got X squared again, which is nice, over 0.0667 minus X. And I know what you're going to be tempted to do. You're going to be tempted to put this number. But that is wrong.
Oh.
Because that number is the acid dissociation constant for acetic acid.
We're not doing that.
This is not acetic acid. This is acetate. It is a base. You need a Kb.
Oh boy.
But Mrs. Gunlock, where are we going to get a KB when all they gave us was a KA?
They give you KBs in the back of your book too.
That's not, no, there's no back of the book here. We can figure out the Kb.
I like the back of the book answer.
No, not back of the book.
Oh no.
We got a Kb, we have a Ka. You remember this? There's a formula.
KB times KA equals 14.
Kw.
KW.
Kb times Ka equals Kw. So what we end up with is Kb equals Kw over Ka equals 1e negative 14 divided by 1.8 e negative 5. You've got to remember to do this step to put this number here because that one is wrong. By the way, this number, as it turns out, is 5.56 e to the negative 10, which is another number that you end up half memorizing because you see it at the end of the titration problems all the time. You kill the x. X is less than 5%.
Change out the KB now.
KB.
That makes me happy.
And that's going to be 0.0667. We'll come back to it. And we multiply these and we square root them, and you end up with x equals some number. 6.089 e negative 6. That is x,
Which is the OH.
which is the hydroxide ion concentration. So, sure, take the negative log. But what is that?
POH.
That's your POH. And that's going to be 5.215. And so how do you get your pH?
Subtract it from 14.
Subtract it from 14.
If If you don't know, say 14.
Yeah, 14 is, or 1E14 is really common. 8.784 equals the pH, which if you had gotten a pH of 5, you would have gone, why is it acidic? Hopefully. And realized it's not acidic, it's basic. That's your POH. Anyway, so there's your pH. Bam. So that's E. One more.
Should you check it?
Fine, I'll check it. Fine. I keep forgetting. Man, I'm going to lose points all over my test.
I am so good to you.
What? No, you're not.
Hey.
And you end up with what? What do we got? We got some tarot. I didn't even do it on my paper.
Again.
6.089 E negative 6. Yeah, I know, right? Divided by 0.0667 times 100. But it looks like it always succeeds. Why do I have to do it if it's always... It doesn't. It's not always.
Because it's
Every now and then it'll come up and you're like, oh no, I have to go do the quadratic equation. 0.009%. Boop, 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 boop. Bing. Okay. F.
Maybe we don't have to do F.
Oh, we got to do
no
F.
room.
There is no room. Where are we going to go? Where are we going to go? We're going to go over here. F.
Oh no, she made
I found room.
I
All right.
tried.
F is with 250 mils of 0.1 molar KOH. And we've got to do the stoichiometry. Here we go. The acid and the base and the neutralization reaction. What are we doing? K, that's a K. K. Potassium acetate. B4, A4. And that's 0.02. This is 0.025.
Oh.
This is a new situation
Oh.
in which we use up all of our weak acid.
Oh.
And there will be remaining strong base. 0.005.
Ooh.
0.02. Okay? Moles, by the way.
My brain just went.
Yeah, I know. Your brain does that a lot. All right. So now, let's go do our ice chart. But maybe it's pointless. Shh, don't tell them yet. All right. This is the same ice chart that we did in E, because what we have is weak base, not any of the acids. So you've got to do the backwards one like we did up there in E, where it attacks water and steals the hydrogen ions. And we've got this, which is 0.02 moles over 0.350 liters. We don't care about water. We don't have any of this. We do have this. It's here.
It's 0.05.
Yeah,
Ooh.
it's 0.005 moles over 0.35 liters. It's important to notice that we do have that. All right, so the change, we lose some of this, we gain some of this, we gain a little bit of hydroxide ions, so that's 0.057 minus X, this is X, this is 0.014 plus X. So we do our fun math with the 5.56 e to the negative 10, which is our KB, if you remember, equals X times 0.014 plus X over 0.057 minus X. We can discard. We need to check later, which I'll probably forget. And we find that X is equal to, what's X? Where's X? X. Here it is, 2.2637 e to the negative 9th. So that's X. And then you kind of go, all right. X is our weak acid, and X is here, the hydroxide. So this goes on that, right?
Right.
So what's your hydroxide ion concentration is 0.014. 1, 2, 3, 4, 5, 6, 7, 8. 22637. There's this. This is the contribution from your weak base, and here is the contribution from your strong base.
I don't think the weak base matters much.
The weak base doesn't matter much. So what's nice is that in this case, you have excess strong base. So what is driving the pH? The excess strong base.
Well, but there's like 0.0000002 something from this guy.
Yeah, you know what?
It doesn't
Whoop-de-doo. So when you have excess base sitting there, that's what's happening when you've got this thing, right, with your titration. Here is the buffering. Well, that's the strong one, and here's the weak. Here's the buffering section where the pH doesn't change very rapidly. Here's the half equivalence point where the pH equals the pKa. Here's the jump. Here's the equivalence point. Okay, there's your jump in pH. And this jump in pH, that's where it's driven by the strong base. Right when you go over, the strong base takes over. And it rapidly drives it up to a pH of 12 and 13 or whatever. And it just sort of stays there after that. And after the equivalence point, your weak base doesn't matter. Your weak acid doesn't matter. It's the excess strong that matters. If you notice this, you don't have to do that.
Cool.
You can just do negative log of 0.014 to get your pOH instead of bothering to do the negative log of 0.01400002267. If you do both of these, it's kind of funny. Your pOH when you're just doing the strong is 853 871964, and your pOH when you are doing it with the strong and the weak is 1.853871894. There, right there. Bam. There's the difference.
Yay.
Yeah, anyway, the decimals cut off here.
Oh.
So,
Nice.
there you are. And now we're done.
Really?
That was, how long was
That's
that? Was a half-hour problem.
That was pOH.
Oh, fine. pH is 14 minus 1.85, and that's equal to some number. I don't know.
Can't believe you're doing that on the calculator.
12.15. Okay?
In this case, does X matter? And do you need
U
to check
and X and XEXX. No, not really, because we've proved that we don't have to do this anyway. So, yay.
it? Woohoo!
Enjoy.